just like for the hydrodynamic boundary layer we have solved the hydrodynamic boundary layer equations by using the integral method, we will see the corresponding integral method for the thermal boundary layer equation or the energy equation for the thermal boundary layer. So, we will begin with that. Integral method. So, we will begin with the thermal boundary layer equation. As a first step, what we should do, we have already done the same thing for the hydrodynamic boundary layer equations. Now you tell that what should we do for the thermal boundary layer equation. Integral method, what we are doing, basically we are integrating it with respect to y across what? Across the thermal boundary layer for the energy equation. Now, we will integrate this by parts. This is the first function and this is the second function. So, this will be first function into integral of the second minus integral of derivative of the first into integral of the second. And we can make a further simplification. In place of del v del y, you can write as minus of del u del x from the continuity equation. Therefore, this equation becomes integral of u del t del x 0 to delta t. We can club this term and this term together plus t del u del x plus v at delta t into t at delta t minus v at 0 into t at 0, that is this term. This is equal to the right hand side Now these two terms together become del del x of t into u or u into t. This term is 0 because V0 is 0, no penetration boundary condition at y equal to 0. So, we have to estimate what is V at delta t. So, how do we estimate what is V at delta t? We will use the continuity equation and integrate the continuity equation across the thermal boundary layer. So, continuity So, from here we get V at delta t is equal to minus what is t at delta t? What is this? This is practically T infinity. So, we can write right hand side, what is the temperature gradient at delta t? 0, because there is no further variation in temperature. So, this becomes minus see, just like the momentum integral equation gives the wall shear stress directly, this equation gives the wall heat flux, because minus k del T del y at y equal to 0 is the heat flux at the wall. It gives it through some integral expression, and as we have seen that if we use an approximate temperature profile just like approximate velocity profile, then the result may be erroneous for the velocity or temperature, but integral of velocity and temperature it is not so erroneous, typically because we are using some complementary like some function into 1 minus that function, something like that. So, with this understanding, we have combined these two terms. Because T infinity is a constant, we can take it easily within and outside the derivative without any problem. Next, our issue will be whether we can bring this derivative out of the integral or not, and for that we will use the Leibniz rule to check. So in this example f is u into T infinity minus T. A is 0 and B is delta T. So what is fxb? What is fxb? That is f at y equal to delta t, 0 because t is T infinity. At y equal to delta t, t is T infinity, so this term becomes 0. What is the other correction term? This is 0 because A is 0, so dA dx is 0. So that means here also we can, just like what we could do for the momentum equation, we can take this out of the integral without any problem because the correction terms are 0. So we can write this equation is called as energy integral equation. So we can write this equation in terms of non-dimensional velocity and non-dimensional temperature. So if you define theta is equal to T minus T wall by T infinity minus T wall. The purpose of defining theta in this way is that this has similar scaling as u by u infinity. See, u by u infinity 0 at the wall and 1 at the edge of the hydrodynamic boundary layer. This is 0 at the wall and 1 at the edge of the thermal boundary layer. So u by u infinity and theta have the same scaling. So if you use this non-dimensional temperature, then you can write ddx of u So we have added and subtracted T wall. So this becomes ddx of 0 to delta T u into 1 minus theta 1 dy is there. This is the energy integral equation in terms of the normalized temperature. So we will make an assessment of the situation using the two limiting cases as we had done for the similarity solution. One is Prandtl number much less than 1 and the other is Prandtl number much greater than 1. So case 1, so Prandtl number much less than 1 means delta is much less than delta t. So if this is the delta t, then your delta is much less. So almost throughout the thermal boundary layer U is U infinity. So U is approximately equal to U infinity almost throughout entire thermal boundary layer. So that U part is there. What about theta? So theta, just like we could use approximate velocity profiles for the velocity for the momentum integral equation, similarly we can make use of approximate temperature profiles. So as an example, this kind of velocity profile we had taken for the momentum integral equation, similar thing we are taking for the temperature. You could take other profiles, but you have to find out the constants based on the essential boundary conditions. So what are the boundary conditions in terms of priority? What is the most important boundary condition, or what are the most important boundary conditions? So see, at least two constants, if those are there, those should match the values at y equal to 0 and y equal to delta t, that much should be there. So at y equal to 0, what is theta? Theta is 0. At y equal to delta t, theta is 1. Then at y equal to delta t, del theta del y is equal to 0. And the fourth one, at y equal to 0. So if you look into the equation, u del t del x plus v del t del y is equal to alpha del 2t del y2. So at y equal to 0, both u and v are 0, therefore this must be equal to 0. So in terms of theta, so you can see that if you cast it in proper non-dimensional form, the boundary conditions look like exactly the same as those were for velocity when we approximated the velocity profile using this form. Therefore the constants will also be the same, because the similarity is a mathematical similarity. Mathematics does not understand that one is heat transfer, one is fluid mechanics. If you bring exact similarity into picture, the values will also be similar. So you will get theta is equal to, what was the velocity profile? 3 by 2. Now instead of y by delta, it will be y by delta t for the temperature profile minus half y by delta t whole cube. So if you work out this by substituting these conditions, you will find out exactly this. So we will substitute that here in this equation, d dx of integral 0 to delta t u becomes u infinity to 1 minus theta okay. So we have substituted the temperature profile in the energy integral equation. Then let us assume y by delta t is equal to eta. So dy delta t into d eta. So d dx of this is equal to 3 alpha by 2 delta t. Now we will integrate this so So if we do it quickly, u infinity d delta t dx so this becomes 8 minus 3 5 8 minus 6 2 plus 1, so 3 by 8, right, 3 by 8 so delta t d delta t dx Now what is the boundary condition to get so this is dx So if we integrate this, then delta T square is equal to 8 alpha x by u infinity plus some constant C1. So question is, what is the boundary condition to get this value of C1? What is the boundary condition at x equal to 0? See, this is a subtle distinction between the thermal and the hydrodynamic boundary layer. At x equal to 0, the hydrodynamic boundary layer thickness must tend to 0, but at x equal to 0, the thermal boundary layer thickness may not be 0. I will give you an example. Let us say that this is the solid boundary and this plate is heated starting from here. So this zone is only heated. So the thermal boundary layer will develop from here and not from here. Okay. So the hydrodynamic boundary layer, the frictional effect will be felt from the starting from here itself, but thermal boundary layer, the heating or cooling effect of the wall will be felt only from that location from where you start heating or cooling. So you may have a length x0 which you may say as unheated or uncooled starting length. So we can say that at x equal to x0, delta T equal to 0. As a special example, let us take x0 equal to 0. Example 0. But this is a special example. Don't think that it is a generalization. X0 could be any value, but as a special case we are considering that the entire plate is heated or cooled. So that means you will get C1 equal to 0. So delta T by x is equal to 8 alpha by u infinity x, right. So this is 8 into Reynolds number to the power minus 1 into Prandtl number to the power minus 1, right, because this is u infinity x by nu into this square, right. Because this is u infinity x by nu into alpha by nu. Alpha by nu is 1 by Prandtl number. Okay. So now our objective is to get the Nusselt number. So we will use the boundary condition at the wall. So theta is T minus T wall by T infinity minus T wall. So we have brought this within this derivative. Is it true if the wall temperature is a function of x? Yes or no? Is the transformation from this form to this form valid if T wall is a function of x or not? It does not matter because this is derivative with respect to y, this is not derivative with respect to x. So if T wall varies, at most it will vary with x, but wall is along x, so wall temperature cannot vary with y. So with respect to y derivative, T wall may be a function of x, but still it does not have any dependence on y. So k del theta del y at y is equal to 0 is this means h delta t by k is equal to 3 by 2. Now what is required is Nusselt number, that is h x by k, Nusselt number at x. So this is 3 by 2 and x by delta t from this expression. So 3 by 2 root 8 Reynolds number to the power half into Prandtl number to the power half. If you recall, in the similarity solution it was 1 by square root of pi, right. So you can compare that how accurate this is as compared to that, find the numerical values and you will see that it is the difference is not that much. So actually the integration has smoothened out many sources of error, and that makes the result more or less acceptable. Now I will discuss about one very important point before moving on to the other case, Prandtl number much greater than 1. That important point is that how to get the average Nusselt number. Why average Nusselt number is important? Because Nusselt number is a function of x. So along the length of the plate it will vary. So if somebody asks that what is the average heat transfer coefficient, how will you calculate it? So in other words, what is the average heat transfer coefficient? So you can see that h is a function of x. Why h is a function of x? You look at this expression h, it is a function of delta t and delta t is a function of x, right. So you can write h as a function of x by substituting delta t as a function of x here. So h average is equal to integral of h dx from x equal to 0 to L divided by the total length, and Nusselt number average is based on this h average, okay. So many times this is a calculation that engineers need to predict what is the average heat transfer from the wall to the fluid or fluid to the wall depending on what is heated and what is cooled. So for that h as a function of x gives you the local variation, but you may also be satisfied with the average trend, and for that you have to do that integration. So that being a trivial integration, because delta being a polynomial simple, so delta, how delta will vary with x. So delta square is equal to, delta square is proportional to x. So delta or delta t square is proportional to x. So delta t will vary with square root of x, x to the power half. So the boundary layer profile that we draw is actually x to the power half. The profile of the boundary layer, this one that we draw, it is actually a function of the form x to the power half. Hydrodynamic boundary layer and thermal boundary layer for Prandtl number much less than 1. So delta T as a function of x, when you substitute some constant into x to the power half, that will give you h will vary with x to the power minus half, and then that integration you can do. Okay. Now we will do the next case, which is a little bit more involved than the previous case. Yes. No, that is all right. So your question is that delta T is equal to 0 if the heating or cooling starts from here, there also it is 0. But your problem of growth of thermal boundary layer starts from here. So your domain starts here. This is not a domain of your interest, because in this domain there is no heat transfer. You have to see that what is your domain of heat transfer. So in this domain all temperatures are same. So there is no heat transfer. So heat transfer domain starts from where you have the wall temperature different from T infinity. So within this part of the domain, the wall temperature and T infinity all are the same. So there is no heat transfer. So you have to keep in mind that this equation is applicable in the domain where you have heat transfer. Okay. So that is why you apply with the domain starting from here. Prandtl number much greater than 1 means delta is much greater than delta T. So you cannot say that U is U infinity within the thermal boundary layer. So let U So we start with the energy integral equation. So in this equation we will substitute this U and we will substitute this theta. So we will assume that y by delta T is equal to eta. So y by delta is equal to y by delta T into delta T by delta. Let us say that delta T by delta is equal to a ratio R. What is the value of this R, small or large? What is R, small or large? It is small, right? So this R must be much less than 1. So this we will use for algebraic simplification. Now, when you multiply this term with this term, out of these two, which one will be of dominance? This one will be of dominance because R is expected to be much greater than R cube for small r, right. So, you can write so 3 by 3 eta square by 4 minus 9 by 4 eta cube by 3 plus 3 by 5 eta to the power 5 into 4. R into delta t becomes, so R is equal to delta t by delta. Can you quickly do it and tell me what is the value? So these two cancel, right? So 3 by 20. There is one R, right? There is one R. So R into delta t. So 3 by 20. In place of delta t we can write delta into R, right? So delta R square. Why we are writing this is because delta we already know. We are interested to solve for R, that will give us what is delta t. So 3 by 20 into delta R square right hand side delta t we have written delta into r. Okay. So these 3 get cancelled and this becomes 1 by 10. So u infinity, maybe u infinity we will take in the right hand side. So d dx of, so we can write delta r into d dx of delta r square is equal to ten alpha by u infinity. So now we can write delta d delta dx into r cube plus delta square r into 2r dr dx. Now this delta as a function of x we can get from the hydrodynamic boundary layer equation. So if you recall, if you had completed the exercise of finding delta as a function of x from momentum integral equation, in the momentum integral equation if you substitute u by u infinity is equal to 3 by 2 y by delta minus half y by delta whole cube and integrate it, you will get this delta as a function of x. So we will use this. So delta square by x square is equal to 280 by 13 into Reynolds number to the power minus 1. So nu by u infinity x, right. So delta square is equal to 280 by 13 into nu x by u infinity. So you can clearly see that delta varies with x to the power half, the edge of the boundary layer. So we require delta d delta dx. So if we now differentiate both sides with respect to x, so 2 delta d delta dx is equal to 280 by 13 nu by u infinity. Okay. So that means delta d delta dx is 140 by 13 into nu by u infinity. So let us write it down there. then this term delta square, in place of delta square what we will write, 280 by 13 nu x by u infinity. So here there is one r cube, here you have r square dr dx. So what is d dx of r cube? 3r square dr dx. So in place of r square dr dx we can write 1 by 3 d dx of r cube, right. So let us move on to the next step. So 140 by 13 nu by u infinity r cube plus 280 by 13 nu x by u infinity into 2 into r square dr dx is 1 by 3 d dx of r cube. Is equal to 10 alpha by u infinity. Okay. So u infinity gets cancelled from all sides. If you take the nu in the right hand side, alpha by nu becomes 1 by Prandtl number. So we can write, okay, before that we can possibly simplify a little bit. So 56 by 39 d dx of r cube, 56 by 39 x, sorry 56x by 39 d dx of r cube plus 14 by 13 r cube is equal to 1 by Prandtl number. Just check whether this is correct or not. So we can write d dx of r cube plus 14 by 13 into 39 by 56 into 1 by x. Okay. So this equation, if you take, let r cube equal to z, this equation you can write dz dx plus 3 by 4 x into z is equal to 39 by 56 x into 1 by Prandtl number. So this equation is of the form dy dx plus py is equal to q. So the solution of this equation relies on multiplying with the integrating factor. So let us identify the integrating factor. So integrating factor e to the power integral right. So e to the power three by 4 ln x. So x to the power right. So you multiply both sides by x to the power 3 by 4. And that should give you what is z as a function of x. Remaining is straightforward. See, it is important that you work out each and every individual step, that gives you a lot of confidence. You will see that I mean many books will write from straightforward calculation it follows. So I mean as a student I know that whenever I was a student, never I found that it is such a straightforward calculation as it is mentioned in the book. So you see that the steps that we had gone through, there are many steps which if you had tried to do by yourself, it would have created a lot of problem. And it is important, that is why I have done it up to the stage. From here it is really straightforward, because then the remaining is just after the putting the integrating factor you can get the solution. So you please work it out completely and find out. So this is like the homework that I am leaving on you. Find out the Nusselt number is equal to some constant into Reynolds number to the power half into Prandtl number to the power 1/3. What is this constant? It will if you have done it correctly, it will come out to be something in the range of 0.33, something like that. So please do that, please complete this, but I have done enough number of steps so that I mean the remaining should be easy for you to complete. And I mean essentially for deriving all this, as I told you that these derivations are, these are the problems from this part of the course, and you must learn how to do these derivations. No formula based study please. So if you know or if you learn how to do these derivations, maybe exactly these derivations may not come in the exam, but if you had followed this, you will see with some different velocity profile, some different temperature profile, but the method will be very similar. So please gain some confidence, and as I want to repeatedly tell you that I do not want to discuss anything in the undergraduate class which I cannot derive in the board. So thousands of formula which I cannot myself derive in the board, I cannot expect that you will remember this and you will derive those and all this. So whatever are the essential fundamental things which can be derived in the scope of an undergraduate course, that part of convection we are only covering, and this will give you the foundation for learning the advanced topics in convection. Okay, we stop here today. In the next lecture, so what we have done up to today is we have discussed about forced convection over a flat plate, but in engineering maybe another sort of important problem is what happens for forced convection inside a pipe or inside a duct or inside a channel, not in an open space but in a confinement. So that is called as internal forced convection. So from our next lecture we will start discussing on internal forced convection. Thank you.